Hello everyone. A few questions on chapter 25, calculation of electric potential. Maybe these are not very straightforward questions. That's why I would like to go through them. So the first question is, we have an infinite plane of charge or surface charge density. Sigma is given as 55.5 picocoulomb. Pico means 10 to the power minus 12 divided by meter square, is tilted at 45 angle to the vertical direction as shown below. So this line, this is the infinite plane charge, and this is, let's say, this is the vertical. So we have the angle is 45. The potential difference VB minus VA in volts between point A and B. These 2 points are 4.5 meter distance from each other. So the question simply asks us to find the potential difference VB minus VA, and we have 5 choices, so one of them should be correct. Okay, so first thing, in order to find the potential difference between these 2 points, we simply follow the line integration. We say VB minus VA by definition is equal to negative the line integration or line integral of the electric field between point A to point B. Line integral means ds. Okay, so what do you mean by E here? E is the electric field while you move from point A to point B. So let's say, and ds is the vector on the path that connect point A to point B. Let's say these small vectors are ds. Okay. So first thing we need to clarify that electric field at point A actually is the same value as the electric field at point B. So electric field at point A, value-wise and even direction, is equal to electric field at point B. In general, electric field is equal to sigma divided by 2 epsilon naught. If you forgot to get this relationship or this expression, please review chapter 23, my video on using Gauss law to obtain this equation. This is true if you have infinite plane of charge distribution, surface charge distribution. So it turns out that the electric field actually does not depend on distance, even though point A is closer to the plane and point B is further, right? But because the plane is infinitely large, the electric field at point B and electric field at point A is simply equal value, and is given by this equation. Okay, so simply now we need to evaluate the integral. So this basically, because electric field is constant, I could take it out from the integral, is equal to ds. Now the angle between electric field and the ds, it's obviously is equal to cosine 45, right? Why is that? Because we already have 45 here. Okay, so for example, I'm going to just clarify why this electric field, of course, if we assume this is positive, so the electric field will go this way, right? Electric field, let's say here, will go this way, electric field will go that way. So we know, for example, we know this angle is 45, so this is 45, I mean this is 45, so this one is 45, that's why I put 45 here. Okay, again, the integral is between point A to point B. I forget the negative sign here, so it's equal to negative E cosine 45 and integral from A to B ds. Okay. Of course, if you add all these small vectors, this ds, this, all these ds together, the answer simply is going to be 4.5 meter. Let's just call it s. Okay, so the answer is equal to minus E s cosine 45. So final answer should be minus, and our E is this value, so it's equal to sigma divided by 2 epsilon value, okay, is cosine 45, and this should give us the correct answer. Sigma is equal to 55, 10 to the power minus 12. We have 2, we have 8.85, 10 to the power minus 12. So this is nice, we could cancel 10 to the power minus 12. And S is 4.5. And we have cosine 45. I already calculated this using my calculator, so it's equal to minus 9.979 volt, which I could approximate it as minus 9.98 volt. So it looks like B is the correct answer. B is the correct answer. Okay. Again, you should understand why the physical meaning of minus. Okay. Okay, so let's go to the second question. Here we have a charge of 3 microcoulomb is distributed uniformly along the circumference of a circle with a radius of 20 centimeters. How much energy is required to bring another charge 25 microcoulombs? So we have a circle with the charge of 3 microcoulombs. Let's call it Q, uppercase. And now we need to evaluate or calculate how much external energy is required to bring a charge 25 microcoulomb, let's call it small q, from infinity to the center of the circle. Okay, to the center of the circle. So first we need to draw a sketch to explain the thing. Okay, let's say this is a circle. It's not a perfect one, but let's accept it. And let's call this one point P. So the answer first, we need to find the external energy. Well, if you remember the way we explained the potential and its relationship to the potential energy, we simply said potential, for example, at point P minus potential at infinite basically is equal to, in this case, is V at point P minus 0, because by definition, electric potential at a point very far from the charge is equal to 0. And this is simply equal to work done by the external agent divided by the Q that you want to bring it to that point. So, which means work in this case is equal to Q multiplied by Vp minus V infinite, which basically is equal to Q Vp, because V infinite is equal to 0. Okay. So this is our equation. So we have one problem now. We have to find Vp. This is not difficult. We could find Vp. Now, because this is a distribution of charge, we need to distribute the ring or the circle into many, many small pieces. Each one carry a small charge. Let's take one of them, for example, this is dq. This dq is far from this point by a distance r. Let's call it r. Although r is not given, but we could get it from the, actually r is given, yeah. R is given, sorry. So the potential at point P from that small charge simply is equal to dV is equal to K dq divided by r. But of course, we need to calculate the potential, from all other small points on the ring, on the total ring. So we need to do integration. Okay. Now dq here, I could write it in terms of lambda. So this is equal to K lambda divided by ds. ds, because this is like an arc, so ds is an arc on the circle. We have done similar questions before. So this is ds, this is r, this is d theta. ds is equal to r d theta. Okay, so divide by r, integral. I could take and instead of ds, I'm going to write r d theta. Okay, so it's going to be equal to K lambda r d theta divided by r integral. This will cancel out. Now, because this is a complete circle or complete ring, I should say, so it's from 0 to 2 pi. So the final answer is equal to K lambda 2 pi. But now we don't have lambda, so we need to find lambda. I forgot to say the left-hand side of the equation simply going to give us Vp, so Vp is equal to K. Lambda, here we have a complete a circle or a ring, so is equal to Q divided by 2 pi r. Remember, we have 2 pi. This with this will cancel out, so the answer is equal to K Q divided by r. KQ divided by r. Okay, so let's substitute this into previous equation. That means work required to bring a small charge 25, actually it's not small, the charge 25 microcoulomb to the center of the circle is equal to Q multiplied by this equation, KQ divided by R. So let's double check. So K approximate 9 10 to the power 9. Q, we have a 3 times 25, so 3 times 25. Remember, we have microcoulomb, so it's 10 to the power minus 12. We have R is 20 centimeters, so it's 0.2. If you calculate this, this should give you actually give you very good approximation as 3.4 joules. Okay. Looks like there is a mistake. I feel that it has to be smaller than joule. Let me calculate using my calculator. Because it's 10 to the power minus 12. We have 10 to the power 9. So you already have 10 to the power minus 12, right? And let me double check. 9 times 75 divided by 0.2. Actually correct. It's B. It's the correct answer. I hope this is clear, and thank you very much for watching.